Hello everybody, welcome back to my channel. Today we're going to look at something interesting here. So we have a paper called Graph Neural Prompting for large language models. And this paper is essentially a new prompting approach that could help you to increase the accuracy of your language models, right? And it's an alternative to your usual knowledge graphs combined with LLMs approach. And it offers higher accuracy in that regard. So let's go through the abstract now, shall we? So, large language models, LLMs, have shown remarkable generalization with exceptional performance in various tasks, but they have their own limitation, right? So it's about the hallucination problem and also its ability to return actual factual knowledge, right? So, and there's a lot of different approaches, such as using knowledge graphs, right, with the LLM and do some kind of a joint training process together or customizing their model architectures. And obviously, the downside to this kind of approach is that when you're doing this kind of fine tuning approach, it is simply very expensive, right? So the question of how to enhance pre-trained LLMs using grounded knowledge, such as retrieval augmented generation (RAG), is an open question. So this paper is gonna be it's gonna try to address that problem, uh, and their solution is called graph neural prompting, a plug-and-play approach to help the LLMs to learn beneficial knowledge from knowledge graphs. So it is essentially a new approach to fine-tune the currently existing LLMs using knowledge graphs, right? So, okay, graph neural prompting uses different designs, such as a graph neural network encoder, a cross-modality pooling module, a domain projector, and a self-supervised link prediction objective, right? And obviously, they've done a lot of experiments on their approach, and here is their GitHub link right here. If you are interested, please do go and check it out. But for now, let us go straight to the conclusion if they have to see if they have anything more to say. Okay, so in this paper, they address the limitations of LLMs in capturing actual knowledge, and they propose their new approach, graph neural prompting, and it's really good in learning knowledge from knowledge graphs. And they tested it on common sense and biomedical reasoning tasks, and it shows that it can improve the performance by up to roughly 14% when the LLM is present, and plus another 2% when the LLM is fine-tuned, right? So yeah, it seems to be promising from the conclusion. So let's get into the introduction here. So okay, so in the introduction, they talk about how LLMs are really good in like Q&A, summarization, and they have some emergent capabilities, but this emergent capabilities claim has been sort of debunked recently, if I'm not mistaken, but it's really up to debate here. So, okay, right, blah, blah, blah. Okay, so beyond the conventional approach of fine-tuning the LLM models, where all the parameters are adjusted, right? A group of researchers have proposed prompt-based adaptation methods to modulate the frozen LM's behavior using just prompts, right? So rather than just changing the LM parameters using gradient descent, how about if we just use some kind of a way to adjust the prompts, right? In this way, it would be much cheaper, right? So, okay. Yeah, it is say exactly that, right? So rather than adapting the parameters, rather than changing the parameter, rather than updating the parameters in the language models, right? These prompt-based approaches frees the LLMs and introduces additional trainable parameters, right? And of course, freezing the LLMs means that you can afford to make adjustments without having to break your wallet, right? So, okay, on the other hand, despite the success of LLMs, they still have limitation in language modeling with regards to returning actual true knowledge here. So, okay, so, and here comes knowledge graphs. So knowledge graph is a graph topology that stores information in its nodes, and it represents connection between different ideas or nodes in using edges, right? And each edge can be different types of connections or relationships. So, okay, so obviously, there are already plenty of ideas on how to incorporate knowledge graphs to help the LLMs to be more factually right. Okay, and then talk about like, oh yeah, there's a joint training process there, but it's difficult, right? Because you have to update the LLM parameters, and it's very expensive and time consuming there. Okay, and the other approach is to just use the knowledge graphs for retrieval augmented generation. So, so that's another way, and it works by feeding the knowledge graph triplets into the LLMs directly. So if you don't know what a knowledge graph triplets uh, is, okay, so it triples, right? So if we go to this website here, okay, it is basically right a set of a subject, a predicate, and an object. So for instance, right here, we can represent this as a subject being John, a predicate being A, and object being doctor in this case, right? So okay, but they argue that this kind of easier approach can introduce some noise, given that knowledge graphs might contain illogical context. So they ask this question: can we learn beneficial knowledge from knowledge graphs and incorporate them into pre-trained language models? And here's what they want to find out. So to answer that question, they propose graph neural prompting, a method to help the pre-trained language models in learning beneficial knowledge from knowledge graphs. So what it does is that it takes and encodes the grounded knowledge to create the graph neural prompt, which is an embedding vector that can be sent directly into the LLMs to guide it to make accurate generations, right? So it first used a graph neural network to capture and encode the graph, uh, the knowledge graph into the node embeddings, right? Then after that, it uses a cross modality pooling module, right, to see the most relevant node embeddings with respect to the text input, right? So that's this part. And it combines all of these node embeddings together to form a graph level embedding, which I would assume would be some kind of an aggregation operation going on here where you do some kind of a sum or something like that, right? And after that, right, it uses a domain projector to breach the graph embedding and the text embedding, I would assume there, right? And finally, it uses a self-supervised link prediction objective so that it can train the model to better understand the connection between the different nodes or the entities in this case, and to capture the knowledge graph in a self-supervised fashion. All right, so okay, so that's the methods briefly, and I also talk about their results. But right now, I think what we should do is that we should go straight to the preliminaries right now because we will take a look at the results later, right? Okay, so okay, so how do you define a knowledge graph? So a knowledge graph is essentially a set of entities, relations R, and the triples, right? T, which is represented by T, right? And now, okay, and now they formally state, okay, so they formalize the definition of multiple choice question answering, right? With these notations here. And okay, and now we shall look at the methods now. So let's see about this. Okay, prompting LLMs for question answering. Okay, so I would assume you guys know what prompting is. It is just writing up some text and feeding those texts into the LLM and see what kind of response you can get from the LLM. All right. So, okay, I see, I see. So here, okay, let's go through this. Okay, so they talk about what prompting is and the typical approach of prompting, and they say it's simple. So, okay, and they kind of formalize it, right? So, okay, define a question Q and give it some context C and the the answers, the options there, A, and we first concatenate C, Q, and A into a sequence of text tokens, right? Okay, and then the design set of prompts, prompt tokens P. Okay, and then they add it right to the input text token X would be later considered to be as inputs for the LLM to generate a prediction. So we can treat the LLM as some sort of a function which takes in both P and X to produce your Y prime here. So yeah, and you can obviously fine tune or train the LLM for downstream tasks using a maximum likelihood loss using teacher forcing, right? Which is basically a fancy word for they just train it. So okay, right, okay, and they go for it like this. Okay, so they define this cross entropy loss equation here, where P is the probability distribution parameterized by the model, right? So the model defines the probability distribution, right? Because you have to think about it, right? It has this softmax operation at the end, right? Which tells you the probability of the token being a specific word or something like that. So okay, so prompt P can be either a hard prompt in which is basically your text input, or a soft prompt, right, which is essentially a learnable embedding vectors, and you can set that up in PyTorch, right? Torch dot nn dot embedding something, right? So okay, unlike existing approaches that uses text as the hard prompt, okay, and now here comes their contribution here. Their graph neural prompting approach encodes structural and factual information contained in the knowledge graph into a soft prompt. Okay, so essentially, if you imagine the entire graph, we can convert it into a embedding vector, and that will be used as the soft prompt for the LLM to take in, right? So it is essentially a sequence of trainable vectors that can be combined with the usual input tokens, right? So, okay. So the learning of P is encouraged to provide rich structural information and knowledge from the knowledge graph, as well as task instruction for each data instance. Okay, and now they talk about subgraph retrieval, right? To semantically align the input text tokens, okay, so they want to align the input text tokens with the knowledge graph. They have to retrieve subgraphs of the entire knowledge graphs that contain relevant entities, right? So for instance, right, for each answer option AK, its corresponding context in Q, we first obtain a set of matched entities with via entity linking to match the tokens in X to the entities in the knowledge graph. So they get the knowledge, the subgraph based on the entities in the match set by including their two hot neighbors. So what they mean by two hot neighbors is essentially if you have a main node right here, imagine this, right? And if it has like another neighbor, this is called one hop. So if its neighbor has another neighbor, then that's essentially two hot neighbors with respect to the main node. So okay, and the relations that connect them. The retrieved subgraph contains the knowledge to help the model in answering the question. All right. So here it is, the meat of the paper, graph neural prompting. Okay. So we start off with the graph neural network encoder that their approach uses. So okay. Although the retrieved subgraph G prime contains rich contextual information regarding the question and answer, some entities and relations are not relevant to the actual question. Okay, so they're trying to address this problem. Directly feeding array fact triples in G prime can introduce noise and prevent the model from concentrating on the useful information. Therefore, they introduce a graph neural network to encode the most relevant information and integrate complex relationships. So, okay, they first have to initialize the node embeddings using some pre-trained entity embeddings. Then they use a graph attention network, right, as their encoder for the subgraph that they have, right? And all of it can be formulated as this equation right here, but you get the node embeddings from applying the GNN to the subgraph, right? So okay, and that's that. And next step, we have cross-modality pooling. So okay, and they say, right, in order to identify the most pertinent nodes in relation to the question, right, consolidating the node embeddings into a complete graph level representation for subsequent use. They created this cross-modality pooling module. So basically, they use a self-attention layer to dynamically identify node significance using internal graph characteristics and implicit interactions among nodes. So it is essentially applying self-attention to the embedding that we got from the GNN right at the top in order to produce H2. So H2 is the node embeddings obtained after calculating self-attention. So essentially it's like a weighting implicitly, I think. So okay. Then they use the text prompt to calculate the importance of nodes within the graph, right? They do this by having a dictionary in the LLM to obtain the text embeddings for every token in the input text, right? So to start by applying a transformation to the text embeddings T and get the transform embedding, ensuring that the dimension matches with the dimensions. And after that, they calculate the cross modality attention using H2 and T prime. So they use H2 as the query and T prime as the key and the value, which is all represented in these two equations here, right? So hold on 1 second. Yep. So that's that. And then you apply softmax to H and the other terms to get H3. Right. So, and finally, right, finally, they generate the graph level embedding by doing some kind of a average pooling operation on the node embeddings H3 in the subgraph. And by doing so, you get H4, which is the graph level embedding, right? And that's exactly what you need right now. So, okay. So how about domain projector? So domain projector, right? So what they want to use the domain projector for is that it is essentially it maps the graph level embeddings that we obtain from H4, and we want to translate it into the text domain such that the LM can actually understand and use it, right? So okay, so how it does that is by a series of neural networks, right? 2 feed-forward networks with an activation function in between, and you get Z, which is your graph neural prompt. And that's pretty cool, right? So the overall idea is quite simple. At the end of the day, you just want the graph neural prompt. Okay, so lastly, we have a self-supervised link prediction. Okay, and they argue that while the downstream cross-entropy objective enables the model to learn and adapt to the target data set, they want to include this link prediction task in order to further refine its understandings about the relationships between entities and, and overall maybe to increase the accuracy, right? Okay, so what they do exactly here, right? In order to predict the link, in order to let the model try to predict the links as an auxiliary task, you basically have to mask out some of the already existing edges in the subgraph, and we force the neural network to predict them, right? Because if it can predict those links, those edges, right, it would have understand its problem even more, right? And this is some kind of an approach that I have been seeing in the past few papers, which I talk about. In those papers I talked about before in my earlier videos, so do check them out if you want to. So yeah, it does help it to learn the graph structure much easily, right? And now, okay, and then they have their mathematical details here, right? So, okay, having mask out edges in the set, and then, okay, given the learn node embeddings of the head entity and the tail entity of the triplet, right? So they can adopt a knowledge graph embedding method called dismilk to map the entity embeddings and relation in the knowledge graph to vectors. And then they can define a scoring function to generate scores for the triplet, for the triple, right? Okay. So blah 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 blah. Yeah. So see, essentially, at the end of the day, you want to get this loss term right here, which is the link prediction loss term, right? And it contains S positive and S negative, right? So S positive is the score for correct positive triples, and S negative is the score for incorrect negative triples, right? So with this loss term, what you essentially want to do is to plug it into the optimization function right here as an auxiliary loss. But it's not the main thing, right? So you have to put in a lambda term, which you can test out during hyperparameter optimization, right? So, okay, and that's it for the methods. Now let's take a look at the results here. So from what I can tell here, okay, so this is the overall result on common sense and biomedical reasoning tasks. So the best results are highlighted in bold, right? So delta PT and delta LoRa represents the relative performance improvement of our approach to prompt tuning and low rank adaptation. Okay, so it is going against the low rank adaptation as well. Right. They also include the full fine tuning result in gray color. Right. And asterisk means multiple prompt design methods are evaluated while only the best is reported. Okay. So from what we can tell here, right? So as far what, what we can tell here, it seems like, okay, GNMP is winning in all tasks, the common sense tasks and the biomedical reasoning tasks, right? So the average improvement is pretty good for the frozen LLM, right? Right. So, but as you can see, if you compare it with like the fine-tuned LLMs, it seems like the accuracy improvement is actually like lower, and in some cases it's not that significant, right? Um, yeah, yeah, it's like Laura and this, right? And then all and then yeah, and what we found out, right, is that although graph neural prompting works quite well, right, when you compare it to like the non-fine tuning options here, but when you actually need to like compare it against the fine tuning options, it is much better for you to like do GNP plus low rank adaptation fine tuning as well. But even so, right, the accuracy improvement is kind of minute compared to LoRa in some cases. So I would just say that if you can afford LoRa, then you probably don't need to worry about like incorporating GNP. But that's my take from it. Okay, so that's all for T5 extra large, which is 3 billion parameter, not really that large anymore. But if we compare it to the 11 billion parameter model, right? The accuracy improvement, right? If we compare it in terms of like the fine-tuned versions, right? It is actually lower. Yeah, it's actually lower. If you take a look here, improved by 3.73%, but this one is 1.13%, and it gets much lower, right? How about if we take a look at this one right here, when the LM is actually frozen? Interestingly enough, right? If we, yeah, so, okay, like 10.66% compared to this, right? Which is like 10.53. But as soon as you get to the other tasks, right? These two are higher compared to these two, right? And there's like actual interesting observations here. Yeah, so I would say this, right? That if you are Okay, right. If you are going to use a large model, such as this one right here, 11 billion parameters, right? Then you probably want to use a GNP in this case, right? Because the accuracy, okay, because first of all, right, if you try to fine tune an 11 billion parameter model, it's not going to be that easy, right? If you don't have like really good GPUs. So what you can do is try to use GNP on its own, right? And if you do that, it almost reaches the same um, uh, accuracy range as being fine tuned, right? So I would say GNP should be used if you are dealing with large, really large models, in this case right here. And I'm wondering what would be the effect if we translate this to like 70 billion models, or even the latest one, which is like 405 billion parameter, right? Llama 3.1. But yeah, that would be interesting to see in the future. So, okay, right. And we have, okay, and we have some ablation studies right here. So the moral of the story here is that if you take out any piece of components at all, the performance just degrades rapidly. So yeah, just keep them on, right? Okay. And they also tested some different integrating different model designs, right? Okay, but I don't think that's too interesting in this case. Okay, blah 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 blah. Okay, right, right, yeah, and I'm pretty sure there's a talk about what I found from reading the figures. And okay, figure 4, performance with respect to different number of cross modality pullings. So the more you use them, it seems like the accuracy increases for the 3 billion parameter models for biomedical reasoning, but it's kind of fluctuating. Um, yeah, but for something like common sense reasoning, it doesn't really help the 3 billion parameter model. Instead, it helps for the larger model, which is the 11 billion parameter model. Okay, pretty sure they have some reasoning here. Um, yeah, as you can see, those are the actual subgraphs that they have. Um, okay, and we have the number of GNN layers and how it impacts the accuracy. Yeah, as I expected here, just because you increase the number of GNN layers doesn't necessarily mean that it would improve the accuracy of your model, right? Due to something like over smoothing, it's going to make all the node representation to converge to the same thing, which is exactly what you did not want in this case. Yeah, so the performance is degrading for arc, right? But for the others, it's kind of like going down, but it's, yeah. So the best, right, is somewhere around 3 layers in this case. Well, the only thing that's kind of bad is for OBQA, 11 billion parameter, in which case you need 5 layers. Yeah, so that's that. Right, this is a very cool paper, right? And I think this paper would be quite useful to everyone, including you and I, if you're working with large language models and you want to increase its accuracy. Yeah, so do make sure to check out the GitHub link in the paper, right? And yeah, if you like this video, please make sure to like, comment, and subscribe. And I will catch you all in the next one. Bye.